All right, welcome back to the second of Andy's Bott lectures. And today it's called Abelianization in Quantum Topology.
All right, thanks. Right. Right, so that's the goal for today, is kind of continuing. So in the first lecture, I promised you 4 applications of Abelianization. And last time, we talked about one of them. So let me briefly return to last time. So we talked about the exact WKB method in analysis of ODEs. And there, so I meant to give and didn't give some references. So let me just recall that this method has been developed over over many decades now, starting with like Burroughs, Silverstone, Ekal, many practitioners, and then the precise theorems that I was using last time, as I said, but I should say it again. So they're due to Takai, Koike, Schäfke. I think I did not mention and should have mentioned some recent work by Dylan Allegretti and then Nikita Nikolaev. And so I told you about a kind of geometric topological reinterpretation of it, where the basic picture was that we're studying ODEs on a Riemann surface, a second order ODE on a Riemann surface, so call the Riemann surface C. And so here the ODE you could think of as being, if you like, you're studying some flat SL2C connections, some family of flat SL2C connections that come to you in the form of a Schrödinger equation. And we wanted to study their monodromy. And the idea was that the effective way of studying their monodromy is to reinterpret the story as having to do with a GL1 connection, a kind of Abelian connection, living over a branch double cover. Branch double cover of the original surface. And so here the problem, the kind of complicated problem of calculating the monodromy got reduced to the problem of calculating some integrals, some ordinary integrals on here. Well, to be precise, to get the asymptotic series expansion of the monodromy, you reduced each term in that series to some particular concrete integrals on here. Now the key device doesn't go higher? Okay. Okay, maybe I just switch to this side. Okay, so the key kind of the key device that got used in this analysis was ultimately the following picture. So we're studying an SL2 connection on the surface, and the trick was to put the connection, called the connection nabla, in a kind of special gauge. So the idea was to triangulate your surface, and in the context of the Schrödinger equations, the triangulation actually kind of came to you dynamically. You kind of automatically got this triangulation of the surface. Anyway, you drew a picture like this, and then in each triangle, you have a picture like this. That gives you a kind of stratification of the whole surface. And then the picture was that you put your flat connection into a kind of special gauge where the parallel transport was diagonal everywhere, diagonal in every one of the open domains. And then here, you would have an off-diagonal piece, which was, say, upper triangular. And here, you would have an off-diagonal piece, which was a permutation, say, like that one. And having the connection in this kind of gauge, you're able to reduce it to something that happens on the double cover, branched exactly at these points. That was kind of the key technical device. OK, now today I've promised to tell you about 3 other applications. Applications of somehow the same kind of picture. So the 3 applications I promised you were classical Chern-Simons invariants, skein algebras, or skein, let's just say skein relations, knots and links, and conformal blocks. OK, so obviously, if I'm going to tell you 3 things today when I only told you 1 yesterday, I have to dispose of one of them pretty quickly. So let me quickly describe what the story is for the classical Chern-Simons invariants. And then the other 2 we'll kind of do together. So there's the key picture. And now, let's just talk for a minute about the classical Chern-Simons invariants. So similarly, I guess I lower it a little. So suppose I'm given a 3-manifold. So the classical Chern-Simons invariant has to do with a 3-manifold. And in parallel to what we did on the surface, let's suppose that it comes to us triangulated. Maybe ideal triangulation, maybe not. The simplest examples have to do with ideal triangulations. Anyway, suppose I'm given a triangulated 3-manifold, and so we'll just talk about the Chern-Simons invariants of flat connections. So someone gives us a flat SL2C connection, nabla over M. So then, so if you're like kind of the starting point of the quantum Chern-Simons theory would be to study the classical Chern-Simons theory. The classical Chern-Simons theory just assigns a number to this connection. It's a complex number, but modulo integers. Concretely, it's given by a formula. So if my connection is, if I write my connection D plus A, where A is a 1-form valued in SL2C, or SLN, but I guess I said SL2, then the Chern-Simons invariant is given by some concrete formula, so I just feel I should write it. So trace of A wedge dA plus A wedge A, 2/3, I guess. 2/3 A wedge A. So OK, that's a concrete formula, but on the other hand, it doesn't look super easy to actually do it, right? So like if someone gives you a 3-manifold, give you a triangulated 3-manifold, and then you ask, OK, what are the Chern-Simons invariants of all the flat connections on that 3-manifold? That looks pretty hard. So one remarkable thing that's known about this, So it's a fact, which, again, it's due to various people. So I think I should mention Thurston. I think Neumann has maybe the sharpest early formulation of it. More recently, many other people, but particularly Christian Zickert. The fact is that for many connections, for many nabla, so not for every single nabla, but somehow for the most interesting ones in some sense, there's a formula which expresses this Chern-Simons invariant as a sum over the tetrahedra. So you have your manifold, maybe you have it divided into 12 tetrahedra, and then we'll have a sum of 12 numbers, each one of which, up to normalization, comes to you as the dilogarithm of some complex number. In fact, not only complex number, but an algebraic number. So this Chern-Simons invariant, initially there's nothing obviously algebraic about this, but somehow it comes out to be a sum of dilogarithms. For hyperbolic manifolds, you might know a statement. There's there's a related fact, which is that if you have a hyperbolic manifold, which is chopped up into tetrahedra, then its volume is the sum of the volumes of the tetrahedra. Each one of those volumes is naturally expressed as a dilogarithm. This is kind of a complexification of that fact, but with the added feature that it applies to a lot of flat SL2C connections, not only the one that comes from the hyperbolic structure. Anyway, so there's this formula, this known fact about Chern-Simons, and all I want to say about it is that this formula also fits into this kind of philosophy of Abelianization. So, how would you actually compute this number? Okay, somehow you have to do this. Somehow you have to do this integral, and the idea is that, roughly speaking, that integral is easier to do if you put the connection into a gauge like this. So, so one can derive this formula using a sort of 3D version of the special gauge we used in 2D. So you make exactly this picture, except now you take, so this is like the picture on the face of each tetrahedron, and then you take the cone over that, and so now you have a three-dimensional picture with kind of codimension 1 walls. And now you can put your connection in some canonical gauge where, again, it's diagonal in most places, it has unipotent jumps, and then it has something tricky that happens at the center of each tetrahedron. And then when you go to compute this Chern-Simons invariant, essentially what you get is you get 0 from everywhere in the picture except the tiny neighborhood of the center of each tetrahedron, and those give you precisely these dilogarithms. So in particular, these xi, so the meaning of these numbers is not very clear from the point of view of the original 3-manifold somehow. But once you have this kind of Abelianized picture, so again, as it was in the other case, we get a GL1 connection, nabla twiddle, over a branch double cover. Now it's a branch double cover of 3 manifolds. And these variables xi show up as the holonomies of this abelian connection nabla twiddle. So in yesterday's talk, kind of the key variables for analyzing the monodromy problem, the key variables were the monodromies, not of the original connection, but of its abelianized version. And here the same thing is true. So these abelianized holonomies are the things that show up in the dilogarithm formula for Chern-Simons. And so so we developed this picture in a joint work with Dan Fried. So we thought of this as really a story about 3-dimensional topological field theories with global symmetry. But anyway, this is one consequence, is kind of this way of thinking about these dilogarithm formulas. Yeah. Yes, that's right. That's right. So you can triangulate the manifold in different ways. Right. So there's like the 2-3 moves and the 1-4 moves. And then that's right. So what has to happen is that this formula, you can write this single invariant as a sum of dilogarithms in several different ways. The 5-term identity is involved. And of course, one thing that I'm hiding here is this dialog is a multi-valued function. So here I should really tell you how you choose the branch, and it's rather intricate how you choose the branch. In fact, that's another place where I think this point of view is kind of helpful, because the way that you really think of this computation is that what you're doing is you're studying the GL1 version of Chern-Simons theory on this double cover. And from that point of view, all the tricky choices about choices of branch turn out to be related to how you trivialize a line bundle over the double cover. That kind of automatically takes care of all the branches and stuff. Yeah. OK. OK, so that's all I'm going to say for now about the 3D Chern-Simons story. And I want to spend the rest of the time talking about these two. So let me tell you about conformal blocks, and the skeins will sort of show up along the way. So first thing, I think I have to tell you just what is a conformal block. And so I'm going to discuss actually two versions of conformal blocks, a sort of easy one, which will live on a double cover, and a hard one, which is the one we're really interested in, the one we ultimately want to get. So let's start with the easy one. So, OK, so conformal blocks. So let's fix a Riemann surface. Call it C. And we're going to decorate our Riemann surface with some marked points. So what is a Heisenberg block? So that'll be the first. This is going to be the easier kind of conformal block. A Heisenberg block on C. Well, it's a bunch of numbers. So it's a collection of numbers. And you think of these numbers as being the correlation functions of some quantum field theory. So I'll often call them correlation functions. But as far as the definition goes, they're just some numbers. Here's the notation for them. I write j of p1 up to j of pn. So here's maybe the point p1. Here's p2 up to pn. For p1 up to pn points of the curve. So roughly speaking, I'm giving a function depending on the data of n points of the curve for any n. So all n, I mean. Except the reason why I don't quite call it a function is because of a little technicality, which is that it actually depends on more than just the points. It also depends on the choice of a local coordinate system around each point. So each of these points, you imagine that you've got a little coordinate system on a disk around it. And so to keep track of those coordinate systems, when I'm being careful, I'll write z1 here. So z1 is local coordinate on this disk, up to zn, which is the local coordinate on this disk. And given that data of the points with their little local coordinate systems, we're supposed to have a number. OK, and then of course that definition so far is very weak. So these numbers have to obey some relations, some conditions. And the conditions are like this. So first of all, they depend holomorphically on the pi. So if I move one of these points within its little coordinate disk, I should have locally a holomorphic function, as long as all pi are not equal to pj. And then it'll be meromorphic when the points collide. But the singularity, the kind of singularity that you get is of a specific kind. So they obey a relation. And the way I'll write the relation is like this. I'll say j of p, j of q. So suppose I have 2 points, and I use the same local coordinate system around both of them. So call that coordinate system z. And now I imagine that the 2 points come close together. Then the relation is going to be that j of p, j of q, having that in the correlator is the same as having in the correlator 1 over z of p minus z of q squared. Plus regular terms. Now, OK. So maybe I should say precisely what I mean by this relation. So let me give you an example. So the meaning is that that relation has to hold inside the correlation functions. What does it mean to say that it holds inside the correlation functions? So for example, if I have, say I look at the correlation function of 3 points, j of p, j of q, j of r, all with the same coordinate z, say. And then I think of the limit where p approaches q, then the statement is that this should be equal to 1 over z of p minus z of q squared. So I've replaced these two by a pole of order 2 with residue 1. And then that's multiplied by the 1-point function with the other insertion, plus regular terms. So in other words, when I take the 3-point function, the singular part of it is determined by the 1-point function. If I took the 10-point function, the singular part of it would be determined by the 8-point function, and so So that's what I mean by correlation functions. There's one more condition. So I said that these correlation functions depend on the choice of a local coordinate. I didn't tell you how they depend on the choice, so they depend in a pretty simple way, actually. So the last condition is that if I change the coordinate, say from w to z, then the effect is just to multiply the correlation function by dz by dw. So in other words, it transforms like a one form in each variable. And so another way I could have said it is that rather than saying it's a function depending on a choice of local coordinate, I could have just said it's a holomorphic one form in each variable. But in a minute, we'll do a more complicated one where I can't easily say it that way. OK, so that's the complete list. That's the complete definition of a Heisenberg block. So a Heisenberg block is, so it's some completely complex analytic definition. It's a bunch of would-be correlation functions depending on insertion of a bunch of points on your Riemann surface. OK, so now there's, so what can we say about conformal blocks? OK, so maybe you don't understand yet why you would care about conformal blocks, but for a minute, just here's the definition. Let's explore it for a few minutes. So the first thing you could say is that whatever it is, so sometimes when we have a Heisenberg block, it's convenient to give it a name. Let's call the Heisenberg block psi. And then when I write these functions, I'll label them. I'll put the psi here to indicate these are the correlation functions of that particular block psi. So then the first thing you can say about them is that they form a vector space. So all the conditions that I wrote are kind of additive conditions, meaning that, and when I write dot, dot, dot here, it just means any collection of these symbols, j of p1 up to j of pn. So if I have two Heisenberg blocks, call them psi and psi prime, I can make another one, psi plus psi prime, just by adding the correlation functions. And similarly for scalar multiples. So OK, whatever a Heisenberg block is, they form a vector space. And so you can ask now, someone gives you a Riemann surface, just what is that vector space? How do I think about that vector space? OK, so the simplest example would be to take, so far the Riemann surface didn't have to be compact, but the interesting case is it'll usually be compact. So suppose the simplest thing would be to take CP1. OK, and if we take CP1, let's see. OK. So suppose I take my Riemann surface to be CP1. I want to give this vector space a name. So I'll call this vector space conf for conformal blocks on the surface. And I'll write Heis. The reason for the name Heisenberg is that, yeah, I should have said. So this relation that I wrote here, so I wrote this kind of formal relation, which is supposed to hold inside of every correlation function. The sort of fancy way of thinking about this relation is that it's the definition of a vertex algebra. So, and this vertex algebra has a name. It's called the Heisenberg vertex algebra. So that's why we call these are conformal blocks, but for that specific vertex algebra, the Heisenberg vertex algebra. OK. So now we can ask, what's the answer? What is the space of conformal blocks? What is the space of conformal blocks on the Riemann surface CP1? And then the answer actually is that the space of conformal blocks is one-dimensional. So this is kind of the boring example. So concretely, it's spanned by a single element. I'll call it psi. Just call it psi. And so in this case, we can completely write down what this conformal block is. So for example, I should write down the 0-point function. So we're allowed to have any number of insertions, including 0 insertions. The 0-point function, conventionally, people put a 1 in here. So let's just take that to be 1. Of course, I'm free to choose it to be anything I want, right? Because I can rescale my 1 generator of this vector space. So let's take it to be 1. That fixes the normalization. Then you ask, OK, what's the next one? So what's j of p z? Well, if you think about it for a minute, you realize that it has to be 0. Why does it have to be 0? Because this is globally what this would be is a non-vanishing holomorphic 1 form on CP1, and there's no non-vanishing holomorphic 1 form on CP1. So that one has to be 0. Then you ask, what's the 2-point function? So let me always write them in the inhomogeneous coordinate on CP1. We have a nice coordinate here. Well, OK, it has to have a singularity, which is 1 over z of p minus z of q, so 1 over p minus q, squared times the 1-point function. The 1-point function is 1. So its singular part should be this. And it would differ from that by some holomorphic object, which has to be 0. So this must be the 2-point function, and so on. So you can determine all of the higher point functions. And they'll just be some simple rational functions that are engineered to have the right poles. OK, so the problem of describing the conformal blocks, the sort of correlation functions of the Heisenberg vertex algebra on a sphere is pretty simple. We've completely solved it. Now you can ask, OK, well, what about for a higher genus surface? So suppose I ask the same question now for a surface of, again, a compact Riemann surface, but now of genus greater than 0. Then it turns out the answer is much more interesting. The space well, OK. Maybe the most interesting thing would be to get some interesting finite number here. So you don't get that. What you get is an infinite dimensional space. And so you can ask, how should we think about that infinite dimensional space? And the good way to think about it is to make the following little observation: that this space, this infinite dimensional space, is acted on by operators. So there's a natural algebra which maps conformal blocks to conformal blocks by operators. So I'll call them L gamma, for gamma, a loop on my surface. So let's draw a picture. Right, the good thing is to, OK, I guess the good thing is to go here. So the idea is this space, it's a big infinite dimensional space, but once you organize it in representation theory, you'll see it's kind of an elementary thing. So here's my Riemann surface. I draw a loop on my Riemann surface. Only the homology class actually matters. So then, if I'm given a conformal block, I need to give you another conformal block, which I'll call L gamma psi. So I have to tell you the correlation functions of this new conformal block in terms of the old one. So the definition is like this. The correlation functions in the block L gamma psi are equal to the correlation functions in the original block psi, but with one added thing stuck in, which is I'll insert one more j, inserted along this loop, and integrated along the loop. And so what I write here is the integral of j of p z dz times the rest, integrate over this loop. So what this really means is that the integral, by definition, it means this. I take the correlation function with one more point and integrate it around the loop. But conventionally, people usually write it like this. You put the integral inside. So you think that that's some new thing that you're allowed to insert in the correlation functions. So then you check that that operation actually preserves the structure of conformal block. It's not so obvious because you would first think, oh, after I insert this thing, I'm going to have a bunch of new singularities, right? I'll have singularities every time one of my points meets this, this loop, and so it won't satisfy the definition of conformal block. But it does, and the reason why is that in the operator product that I wrote down, here, there's no residue. And because there's no residue, there's no singularity when one of the j's approaches this loop from either side. So this is an operation which maps conformal blocks to conformal blocks. And now, so the space of conformal blocks then is a representation of all of these loop operators. And then you can ask, OK, well, what are the relations that the loop operators obey? And a little calculation shows that they obey a relation, which is that if you put them on loops that don't intersect, then they just commute with each other. And if you put them on loops that do intersect, so here this means that, I guess I should use a different symbol. Let's write the intersection, gamma intersect gamma prime. So this means the intersection number of gamma and gamma prime. So if you put them on loops, for example, that intersect once, then they don't commute. They commute up to a factor of, up to a commutator of 2 pi I. So now, so we have this vector space of conformal blocks, but it comes to us as a representation of this kind of Heisenberg algebra generated by the loops on the surface. And in particular, so now you would think, OK, well, the way to study this space then is going to be to diagonalize the action of this algebra. Well, you can't diagonalize all of it because they don't commute, but you could diagonalize half of them. So you could choose a basis of A and B cycles on your surface. So suppose you do that. So we choose a basis, what they call a symplectic marking. So A1 up to AG, B1 up to BG of the homology of the surface, where, satisfying the usual condition, the AI intersect Bj is delta Ij, and the AIs and the BIs have 0 intersection among themselves. So then you can look for conformal blocks which diagonalize all the operators around the A cycles. And it turns out, so those do exist. So we get elements psi x in this space of conformal blocks. For x, so by x now, I mean I'm going to fix the eigenvalues of these operators on A1 up to AG. I can fix them to any numbers. So I'll just fix some numbers, little x1 up to little xg in C to the G. So for any choice of the eigenvalues, I have a corresponding conformal block which has that eigenvalue. OK, actually, I guess I won't use that, so I'll just go back over here. OK, so I'm done with the case of CP1. So I erase that. So we can make these blocks which diagonalize, half of this algebra. So LAI psi x is xi psi x. And then the B operators acting on psi x act by the derivative d by dxi of psi x. So in other words, this is like the usual relation of the Heisenberg commutation relations, right? You have the momentum and position. and you realize them acting on some objects where the position operator is just multiplication and the momentum operator is a derivative. So this problem of studying conformal blocks for this kind of simplest vertex algebra on a Riemann surface, what it's leading to, the answer it's leading to is essentially the quantization of a symplectic vector space. I didn't tell you the construction of these blocks psi x. I think all I want to say about it is that it only uses kind of elementary stuff about Riemann surfaces. So it could be, so given the definition that we've given, that could be like an exercise in an advanced course on Riemann surfaces. The only things that you need are like theta functions and something called the Bergman kernel on the Riemann surface. OK. So just one other thing I want to say about this before we go to the kind of more interesting problem. So the other thing to say about this is, so I introduced these operators that were attached to loops on the surface. There's another thing we could do, which is we could consider, instead of these operators, which obey kind of Heisenberg relations, we could consider their exponentiated version. And I'll put a coefficient b here. So b would be any complex number. Then they obey kind of the Weil algebra instead of the Heisenberg algebra. So they obey like L gamma prime is q to some power, inner product again of gamma and gamma prime, times L gamma prime L gamma, where q, what's q? Q is e to the pi I b squared. So that comes from this relation plus like the Baker-Campbell-Hausdorff formula. OK, and so this is like the Weil. This is like, so if these were the relations of the usual x and p, this is like the relations of the x and the shift operator. OK, fine. So OK, so the point of all this so far is that we formulated some problem of finding correlation functions of a certain kind of quantum field theory, and we can completely describe a huge class of solutions of that problem. Now, let me tell you the problem that the more interesting problem that we would like to solve, that one would like to solve. OK, go back here. So now I want to define the Virasoro conformal blocks, or Virasoro blocks. And the definition will be almost the same as before. So we're going to have a space of conformal blocks where now instead of Heisenberg, I write Virasoro. And the Virasoro, unlike the Heisenberg, has a parameter. And it's annoying. That parameter is also called c. It has nothing to do with the Riemann surface, so little c. C is just some complex number. So it'll be, again, a collection of numbers. So I write them again like, so now the conventional name for the field that generates the Virasoro is T instead of J. So T of Z1 up to T of Zn. Sorry, call them P1 up to Pn. And again, depending on local coordinates. So now I won't rewrite everything in the definition. But the two things that are different are, number one, the operator product relation is different. In other words, the relation that tells you the singularities. So before, I was looking for things that had a second order singularity when two poles, when two things came together, with leading term 1. Now the relation looks like this: T of P, T of Q, again in coordinate z. So now the leading singularity will be of fourth order instead of second, and the coefficient will be this number that I called c, or actually c over 2. So z of p minus z of q to the fourth. And then there's some slightly elaborate sequence of things that come after it. So I'll write it just for the record. So 2t of p divided by, so there's a second order term and a first order term divided by z of p minus z of q, and then plus regular terms. OK, so some funny relation. That relation is the definition of the Virasoro vertex algebra. This is kind of the universal, it's the universal part of any conformal field theory, is it's supposed to have an operator that has this kind of relation. And then to be complete, I should also tell you what's the transformation law. So before, I had this thing that just transformed like a one form. So that was relatively easy to think about. Like we know how to think, well, reasonably efficiently about like holomorphic one forms. I guess I can put it here. So the analogous transformation law for this object, people call the stress tensor, is a little bit more complicated. So if I change coordinates from z to w, the transformation law is like this. So OK, there's a first term which isn't so bad. So the first term looks like it's a quadratic differential. So if I just wrote this, this would be like, OK, I just have a 2 here instead of a 1. So this is like a holomorphic quadratic differential. But it's that plus something else. And the extra term is c over 12 times the Schwarzian derivative of the map from z to w. I guess I'll write the formula for what's the Schwarzian derivative. The thing to remember is it's something which is 0 for Mobius transformations and otherwise not 0. But concretely, just to show you that it's something concrete, here's the formula for it in terms of z and w. So it involves derivatives up to the third derivative of z. OK. OK, so now this is the problem that we want to solve. We want to find collections of correlation functions for this object, the stress tensor, which will have these kind of poles and have this kind of a transformation law. OK, I'll try to say in a second what are the reasons why we would care about this. Maybe right now I should just say there's one reason which comes from physics, which is that literally every two-dimensional conformal field theory, if you factorize it into the left, you can try to factorize them into a part that's holomorphic and a part that's anti-holomorphic. And in the holomorphic part, there will be some correlation functions which behave exactly like this. And so it's useful to be able to understand what are all the possible forms that those correlation functions could have. But now, unlike the case of the Heisenberg, so in the case of the Heisenberg, I could completely construct for you all this enormous set of conformal blocks. In the case of Virasoro, it's much, much harder. So on CP1, you can do it. So on CP1, it's not so hard. So there's, again, a one-dimensional space of conformal blocks. But as soon as you go to a higher genus surface, it's not so easy to produce examples of these things. Now, OK, let's say, so of course, I'm going to tell you some proposal for how to construct these things. But before I do that, let me say at least one of the kind of reasons why people are interested in this thing, besides the physics reason. And that is, OK. Right. So we're going to have, again, some infinite dimensional space associated to a Riemann surface. So this space conf C for Virasoro. That's an infinite dimensional space. And it's expected to carry various structures. In particular, it's expected to be, I won't write expected to be, but it is a representation of, so two things. So first of all, it's a projective representation of the mapping class group of the surface. Projective. And the second thing is that it's supposed to be an actual representation of something called the Kaufman bracket skein algebra. So I'll just write it like, I'll write this name for it. So the Kaufman bracket skein algebra, I'll write skein Q of the surface SL2. What's the Kaufman bracket skein algebra? What this means in practice is that, so for each loop, well, let's say, not only, so the simplest thing is to draw a loop on the surface, but in fact, the better thing to say is you draw a link in the surface cross R. For every such link, you get an operator acting on the space of conformal blocks. An operator on this space conf C or C. And they obey relations. And the relations that they obey, so it's easiest to represent them in a picture. So if you have, I guess the simplest thing, let's think of the picture of the links as, I'll let the R direction be the direction, let's just say it like this. Think of the case where the links are just simple closed curves on the surface. And then if I have two simple closed curves that are just disjoint, that don't intersect with each other, then they commute. Then they give you commuting operators. But if they do intersect with each other, then they don't commute. And then the relation is like this. So I'll say I act first with this one and then later with this one. So the one that acts later is on top. Then the relation is that that's the same as acting with an operator that looks like this. So multiply that one by q to the 1/2 plus acting with q to the -1/2 times an operator that looks like this. I hope it's clear what this means. So the idea is we have two operators. I'm kind of laying one on top of the other. And then the product of doing one and then the other is supposed to be equal to the sum of two terms, where now I've resolved the picture so that now I just have I've combined them into a single link where this crossing is replaced by this picture. And so I have this slightly complicated relation where the product of these two gets expressed as the sum of this one plus this one. So this is analogous to what we had in the abelian case. So before I showed you some operators acting on the conformal blocks for Heisenberg. There, they obeyed a relation which just looked like this. So I didn't draw it in a picture, but I said x gamma prime. So suppose I have the loop x gamma prime. If they intersect, then the relation was that that's equal to q squared times the product where they go the other way. And in fact, it's also equal to q times this one. So this was the picture on the conformal blocks for Heisenberg. It was a representation of a pretty simple algebra, this Weil algebra. And now the expectation for Virasoro is that it produces for you a representation of a much more interesting algebra, this Kaufman bracket skein algebra, which has this kind of relation, where I should tell you what Q is. So here Q was e to the pi I b squared for the b that I wrote. Here you have a similar thing where the central charge C I write as 1 plus 6 times b plus b inverse squared, and then Q is e to the pi I b squared. So some slightly funny relation, but so depending on the value of the central charge that appears in the Virasoro algebra here, you're expecting to get a representation of this skein algebra with this value of Q. OK. And so the goal, what I want to explain to you in the last 10 minutes, is some way of thinking about this complicated problem of the Virasoro conformal blocks by reducing it to the simpler story of the Heisenberg conformal blocks. And so So as with everything I've been talking about, the strategy is going to be to consider some branch covering. So the picture is going to be like this. Suppose we have a surface C and a branch double cover, say C twiddle. So here on this branch double cover, we have this kind of easy problem. What I call it easy. The conformal blocks for this Heisenberg vertex algebra. And here we have the complicated problem that we really want to solve, which is the construction of conformal blocks for the Virasoro algebra. And so the claim is that indeed we can produce these out of these. So we can find a map, I'll write F, which takes the Heisenberg conformal block and turns it into a Virasoro conformal block. OK, and so how do you do it? And so this is joint work of mine with Chen Yu Hao. So how is it done? Well, let me first describe kind of the most obvious thing you might try to do. And something that people have done in the past. So I'll make a map out. It won't be the F we want. I'll call it F0. So the idea is like this. You say, all right, well, to have a conformal block here means I have to be able to give correlation functions involving this Virasoro stress tensor that I called T. And what I have to work with is I'm assuming that someone has given me all the correlation functions up here for the Heisenberg field, which we call J. So I'll win if I can somehow express correlation functions here in terms of correlation functions here. And if you play around a little, you come up with the following thing. You say, OK, well, let's try the following dictionary. Let's take, every time I see T of P, so here's the point P, I'm going to consider the two preimages of that point. And I'll put J at either of those 2 points. So I'll put J of P, call this P1, or I could consider J of P2. P1 and P2 are the two preimages of P. So OK, the precise thing that I should write is I should write 1/4 J of P1 minus J of P2, and then I should square the whole thing. Now, if you think about that for a minute, you realize it doesn't make any sense. Why it doesn't make any sense? Because when I expand this product, I'll meet things with like J of P1 times J of P1. Well, the correlation functions have a singularity there. I'm not allowed to put two J of P's at the same place. OK, so what I do is I just, by hand, remove that singularity. So this is a crazy thing that people do in conformal field theory. It doesn't sound like it should work, but it works. So people call it normal ordering. So the rule is that you have something that's singular, but you also have we're working relative to some fixed choice of local coordinate. So in that local coordinate, you can just expand and throw away the polar part. So that's what you do. OK, then this is at least a well-defined thing. So let's call this dictionary, I'll call it AB for Abelianization. And so my sort of proposed way of making the correlation functions that I want is, so in the conformal block that I'm trying to make, F naught of psi, the correlation functions will be just the correlation functions of the original block up here, but with the operators where I map all the operators from here to here using this dictionary. So here I'll write ab of ... OK, so you can try that. So for example, what does it mean concretely? Yeah, give up on that. Let's go over here. So for example, when I mean the correlation function T of P, T of Q, I'll stop writing the local coordinate now, in the block F naught of psi, by definition, it'll be equal to the correlation function, 1/16 of the correlation function of J of P1 minus J of P2 squared times the correlation function of J of Q1 minus J of Q2 squared in the conformal block psi on the cover. So I take all my operators on the base, I lift them up to the cover, and I compute the correlation function there. if you do that, so then you can ask, OK, well, is it a conformal block or not? Does it satisfy the rules that I had in my definition? OK, so what were the rules in the definition? So one of the rules was that something about the singularity when two insertions approach each other. So when I have two of these t's and I bring them close together. So that you calculate using this rule. And it turns out, so singularities as t of p approaches t of q, they cannot correct. Then you can ask about the transformation law, the coordinate transformation law. And that comes out correct. That's a little funny because here we've got this complicated thing involving the Schwarzian derivative. And in Heisenberg, we just had one forms. So it seems a little bit nuts that somehow you're making this weird thing that transforms with the Schwarzian derivative out of the one forms. So I didn't believe this at first, but this is actually true. It's true because of this goofy process of subtracting the singular part. So I said, when you subtract the singular part, it depends on the coordinate in a kind of tricky way. And that's exactly what you need to get this Schwarzian derivative. So all that so far is something that's more or less well known. It's called the free field construction, or the Sugo. I think in some contexts this would be called the Sugawara construction of the Virasoro vertex algebra. Now, one crucial thing is here I write j of p1 minus j of p2 squared. The two sheets, I just arbitrarily labeled them p1 and p2. Fortunately, what I wrote doesn't depend on that choice, because if I swap my choice of who's labeled p1 and who's labeled p2, I just change this thing by a sign, but I'm squaring it, so that sign goes away. So this is actually a well-defined thing. It's a well-defined thing. It gives you the Virasoro at c equals to 1. So I said that the singularity comes out right. In part of the definition of the singularity involved this arbitrary constant c, and we get it exactly for c equals 1. OK, so now the question is what doesn't work? What's the interesting part of all this? Everything I told you so far, well, it works fine, but it wouldn't be naturally part of this talk if this was the whole story. So what doesn't work is the following. So there's one more thing that we need to check. What we need to check is what happens when one of these T of P's approaches one of these branch points. So there are these, the construction that I gave you makes perfect sense everywhere away from the branch points. It doesn't make sense at the branch points. As P approaches the branch point, as it turns out, the correlation functions in this block, f naught of psi, have a singularity. Kind of unwanted singularity. So we wanted to produce conformal blocks on the surface with no special points. Nothing special happens at any point, particularly nothing special should happen at the branch points of this cover. Yeah, so the idea is we have these insertions of the stress tensor T of P, and the problem is when P approaches one of the branch points. And so I'll just say, since I'm out of time, I'll just draw a picture of how this problem gets resolved. That'll explain why it's part of this talk. The way that this problem gets resolved is is around each branch point, we draw a picture. And the picture we draw is this picture. The exact same picture that appeared in the previous two stories. And we have to insert an additional operator, built out of the J in some complicated way. if you do it just right, you can kind of miraculously cancel the singularity that you had here without creating any other singularities. And it turns out that, so this is like a new way of making the conformal blocks. And okay, in a way that I clearly won't be able to explain here, it's closely connected to the previous story that I told you about Abelianization of flat connections. So in particular, if you want to construct, so I said that there's supposed to be an action of the skein algebra on the Virasoro conformal blocks. And the way you construct that action of the skein algebra is you roughly construct it out of the action of the abelian skein algebra up here. And the map between the two skein algebras is like you have a loop here and you lift it up to here. That's exactly the map that we talked about last time for relating the traces of holonomies here to holonomies here. OK, so all these stories are somehow connected. OK, I think that's all I have time to say, so thank you very much.